Now we're going to start talking about graphing complex numbers. And graphing complex numbers is not a lot different than graphing a regular XY coordinate on an XY plane, except now we're going to talk about the complex plane. So instead of X and Y, we have real numbers that go in what we would normally refer to as the X-axis, and imaginary axis in what we normally call the Y-axis. So when we graph a point, we just use the real value, the A, to go left-right, and the imaginary value, the B, to go up-down. So if we're going to graph the three values in this question here, we're going to start by saying, okay, the first value has 2, which is a real, so that's 2 to the right, 4 in the imaginary direction. So this is the point that we're going to put, but we're not talking about a point here. What we're actually talking about is a vector, which means starting at the origin, so 0, 0, it is the vector or line going to that point. So that is the representation of 2 plus 4j as a vector in the complex plane. So if we do 3 minus 2j, we do 3 to the right, minus 2 is down, so that's this. That's our ending point. It means the vector going to this point. And that wasn't the straightest line. The vector going to that point. -5, well, that's -5 to the left in the real number line. 6 up in the imaginary means this here. And again, we draw the vector connecting those. And that is the vector -5 plus 6j, or the representation of that complex number in the complex plane. Now, we can also add vectors graphically, which will allow us to graphically add complex numbers. In order to do that, we graph the first complex number from the origin, just like we did above. The next complex number, we graph from the tip of the one before it. And what that means is we'll start where the one before finishes. And so this is how we add complex numbers. So the first complex number is -3. So that means -3 in this direction and 0 in the imaginary direction. So there's the first vector. Now, the next vector starts from this point. So 1 means 1 to the right from here in the real direction. That's from this value. So 1. And then 4j means here. So that's this vector added to it. And the answer then, the sum of those two vectors, is actually the resultant vector from the origin to our new ending point. So the blue here is actually the sum of -3 and 1 plus 4j. If we just want to check that algebraically, we can add the two algebraically. We would get 1 plus 4j here. Add them together, that gives us -2 plus 4j. And if we were going to graph that, it would be -2 to the left, so that would put us here. 4 up, and that is indeed the blue vector. So you can see that that correctly added them graphically. If we want to do the difference, what we need to do then is we actually need to change this to an addition. So instead of subtracting, we're actually going to take 1 plus 4j, and we need to add that to the opposite of this, because we don't want to change the minus to a plus. So the opposite would be -3 plus 2j. So now here's the two vectors that we're going to add to represent this difference. And if we go ahead and do that, we end up with 1 and 4 goes to here. There's our first vector. Remember, we start from here now. We're going to go -3, which will bring us back to here. 2 more up brings us to here. So here's the end point. The resultant vector I'll draw in blue again. So what we're saying is that this difference should be equal to -2 plus 6j. And so if we do that algebraically, 1 minus 3 is -2, 4 minus minus is +2 is plus 6j. So indeed, the blue does represent the result both graphically and algebraically. And we can try one more where we do an addition and a subtraction. So first change the subtraction to addition. So we're going to rewrite this first as this vector plus, because we can't do subtraction and we change the signs, this vector plus is okay, so we keep that one the same. And we're going to start by graphing the first complex number. At the end of that one, we start the next, and at the end of that, we start the next. So we start here with 2 and 3, so we're here. And then from here, we're going to go back 1 and down 2, which brings us down here. So we go back 4, 1, 2, 3, 4, and up 4 brings us here. And so the resultant vector, which this time will be in red, is actually this, which is -3 plus 5j. And if we quickly do this, we have 2 minus 1 is 1, plus -4 is -3. 3 minus 2 is 1j, plus 4 is 5j, so the answer is correct algebraically and graphically. The final part of this first set of notes then is solving equations with complex numbers. And we're going to do the exact same thing as we do for any equation, remembering that we want to simplify any radicals first, reduce the powers of j, and then just proceed as if we had any other variables. So for a, I'm going to do the workings just down below here. J to the power of 8, and we're going to try to do this quickly. J to the 8 is j to the 4 times j to the 4, or j to the 4 squared. J to the 4 is just 1. So this is actually simply 4x plus 5 times j to the 4 is also just 1, so we don't even need it, equals 13. And this, hopefully, you can solve very quickly. 4x equals 8, and x equals 2. B, x times the root of -16. So first we deal with that. That's 4j times x plus 3j squared. Well, we should know that 3j cubed. We should know that that's minus j. That's minus 3j. J to the 13. Well, let's see if we can work this out. That's going to be j times j to the 12. Well, maybe we'll write that. J and j to the 12. And j to the 12, maybe we'll speed it up, is just j squared to the 6. J to the 7 is 4j and j squared cubed to get the other 6. And we have an x at the end of that one. Well, let's see if we can simplify this some more. 4j times x minus 3j equals, this is minus 1 to the 6 is 1, so this is 7j, plus, this is minus 1, so this becomes minus 4j to the x. And we move the pieces around, we get 8j to the x over here equals 10j on the right. Divide by 8j. Remember, these are just numbers like anything else. We get the j's that cancel. We get 10 over 8, which is 5 over 4. C, we'll move down here. We have to square this bracket first. So we square it, we get x squared plus 4xj plus 4j squared equals 5 plus 12j. X squared we keep. 4xj we keep. 4j squared is just minus 4 equals 5 plus 12j. If we collect the pieces here, we can use an interesting trick to solve this. On the left, I'm going to leave these, and on the right, I'm going to write it this way. This becomes 9 plus 12j. And we should notice something interesting here. Real number parts, imaginary number parts. So we get two equations. X squared must equal 9 for this to be true, and 4x must equal 12, because the real number parts and the complex number or imaginary parts must be equal. That tells me x has to be equal to 3. Plus or minus 3 for the first equation, but the second equation, only 3 works, so the final answer is simply x equal to 3. Final one then, we'll stick on the side, we'll square it to begin. 1 plus 2jx plus j squared x squared equals 1 plus j minus x squared. J squared is minus 1, so this is actually minus x squared and minus x squared. Those are going to cancel. 1 and 1 are going to cancel. And we're left with 2jx equals j. In other words, 2x equals 1, so x equals 1 over 2. In the next set of videos, we'll start studying the other forms of complex numbers beginning with polar form.